Okay, our next speaker is going to be Kevin Third. But first I want to mention the authors here also. So if we have questions for him after his talk, you can ask him. Hiro Kasano is the author. And in 2001, he worked for Kokuta. It's close, maybe? 2003, he became the domestic assistant sales manager in Japan. In 2005, he became assistant sales manager overseas. In 2007, he moved to change your dresser as a sales manager. Kevin Third, which is presenting, he's been with C&D for 4 years in sales for Southeast United States market. And he oversees all new projects for Cosmo. So, Kevin, the floor is yours.
First of all, I just want to thank you, Daniel, thank Dr. Carrie Gillis, and everyone that was involved with Sheet Welding Metal Conference for having us here. It's an honor. We definitely thank you for that opportunity. Like he said, I'm going to be speaking for Hiro today. He's not exactly comfortable with his English, but I'm from Alabama, so hopefully you'll be able to understand mine. Today we're going to be talking about the importance of electrode management in modern resistance welding. And some of the things we're going to deal with today, we're going to start you out from the very beginning, show you the problem, and then we're going to give you a solution. One thing I did want to mention, unlike the rest of the presentations that we've seen so far, there's not going to be a whole lot of numbers, not technical information. We're going to give you some, but not as much as what you've seen in the past few. We're going to start you out with the analysis of the electrode face, tip management by tip dresser. We're going to talk about the importance of how to choose the correct cutter in tip dressing. We're going to talk about tips for tip dressing and the recommended dressing methods. And we're going to tell you how much you can save by using tip dressers in the future of the automotive tip dressing, auto tip dressing. To start you out with, we're going to talk about why the electrode face will change. And to understand why the electrode face will change, we must first understand today's automotive climate. You know, today's cars are becoming smaller and lighter, but they also must be stronger than ever. And to do this, people are using galvanized steel, high-speed steel, and high-tension steel. And one thing I want you can look up here, you can see that we're dealing with spot welding. You have copper caps, which are very low resistance material, and then you have the steel plates there, which is very high resistance material. When you add gun pressure and weld current there, as you can see, the weld face right there is in good shape to start with. But the more and more that we spot weld, you see how it mushrooms out and how it becomes bigger. Well, the reason is, as you know, copper is very soft, and anytime it's heated up with joule heat, it will expand, and also, after many different spot welds, you're going to have more material pull off onto the face of that electrode. This is just going to be a movie, a slow motion movie of an actual weld nugget taking place. If you see the kind of shiny white material there, in between that, that's where your current will be coming in, and the top piece and the bottom piece is actual copper electrode, and the middle pieces are your steel plate. And like I said, after many different spot welds, you'll start to get a dirty layer of alloy layer on the face of the electrode. And that can lead to inconsistent welds and a change of resistance in your copper. And that's going to lead you to bad welds, sometimes even cold welds. I just want to kind of show you that in slow motion so you can see what is actually taking place. As I said, there's going to be an alloy layer that builds up on the cap surface. We wanted to know, exactly what is that that's on the cap surface. So what we did was we did a study, sent it off to a lab, and found out the actual layer, the alloy layer that is built up. This is after 300 spot welds. I'll just add that. But the alloy layer that was built up was 79% iron, 13% zinc, 6% copper, and a little bit of chromium and aluminum that was also built up there. So that kind of gives you an idea of what was built up. This is also a visual. What we did was we wanted to break down, we superimposed a photo. After 100 welds, you don't see a lot of change. You see about 11 micrometers of buildup there. Not a whole lot of change there. But after 300, look at the jump. You got 87 micrometers there, and you can start to see some cracking and denting in the electrode face. And here's where the big change takes place. After 400, you see 101, and after 500, you see 140 micrometers of buildup. And as Hero likes to call it, air hole forms. After 400 and 500, you see an air hole there, or what we call an indention, or it's dented in. The reason this is so important is because people actually think you'll still be spot welding. So when you go to close down your electrode onto the steel plates, the face is dented in. It won't even touch the steel plates. That causes big problems. It causes cold welds, and your welding quality is not going to be good. This is just a chart basically saying exactly what we just saw in the pictures. As you see, the number of welds increase, the thickness increases as well. One thing I didn't mention, as your welds increase and as the layer increases, and you start to see that indention or caving in or air hole, as Hero calls it, that can cause you to have spatter. That's where a lot of your spatter comes from. This is a chart here where we're looking at the number of welds and the diameter of the nugget. Now, what we wanted you to see was when using non-coated steel, you see it stays pretty stable throughout. There's not a whole lot of change there. As the number of welds increase, the diameter of the nugget stays about the same. But with galvanized steel, after about 1,800 welds, you see it start to get really jumpy, like my hands are right now. But you see it start to move all over the place. And that's what caused inconsistency. You know, anytime we have a problem, if it's consistent, you know, we can usually find a solution. But when we're dealing with galvanized material, you see how inconsistent that is, and that's where we have to have a solution. And we feel like the solution is by using tip dressing. Here we're going to talk about tip management by tip dressing. Like I said, we feel like this is the solution to be able to keep a clean cap face and keep your resistance the same throughout. As you see, before shots of the tip dress, this is after 300 welds. You see how that cap face is mushroomed out. You see how it's got a dirty face there. The weld face is 7.6 millimeters and 7.8 millimeters respectively there in the first two shots. The after picture is after 1 second of tip dressing. It's back down to its original weld face, which is 6 millimeters. So you see it didn't take but 1 second to clean that face up. And you can dress, what we found is you can dress one cap around 40 times each. So you can save a lot of money for that as well. Most of you know what a tip dresser looks like, but we've got an example of one here. This is an inline dresser. Of course, the stand is what the dresser goes on. It holds it in place, keeps it stable. The geared motor there, a lot of people in the past have used AC motors or pneumatic motors. Pneumatic motors. Now most people have gone to the AC motor. And we feel like torque and RPM are the two most important things you look for in your selection of a tip dresser with an AC motor. You also see a switching box. A lot of times in the past, people have used non-fuse breakers and device net, but now going forward, a lot of people are trying to hook up directly with the robot controller. You see the chip collection unit. You know, in today's environmental movement, this is very important. Anytime we do a new installation in a company, they want their floors clean as possible. They also want to be able to recycle their chips. So we have a collection unit that a lot of manufacturers provide. It falls down into this dust box here, and you collect it, turn it back in. That's a good way to keep up with your shavings. And last but not least is the cutter and holder. This is the most important aspect of these things that we're talking about here. The reason it's so important is because there's thousands of different cap figures, there's thousands of different gun figures. You have to get the right one to be able to dress your cap effectively. These are some examples of the outline dressing tools. We're not going to spend a whole lot of time because that's not what we're focusing on today, but these are just some examples I'm sure most of you have seen. There's a manual tip dresser, that's handheld, hook an airline up to it. You have a drill press dresser, use one cap at a time, pull the drill press down, it dresses the cap. The auto tip recycle machine, you can get numerous caps of the same size, put it in, it will sort it out after it's dressed. And of course the ratchet dresser is just a hand dresser. you basically move it with your own hands. So, but like I said, today we're going to focus on the auto tip dresser. This is an example of the inline dresser. We recommend 150 pounds, or 150 kgf of pressure. It's about 300 pounds for 1 second. And as you see, and I told you in the previous slides, after 300 welds or so, is what this test was run off of. We got about 0.12 millimeters of removal there. So we clean the cap up nice, and you're ready to go back and weld again. This chart here is something that we recommend that every customer have whenever they decide to put dressers in line. What it shows you is as the gun pressure goes up, the cutting amount will go up as well. This chart here was based off 1 second of dress time. Torque at RPM, I don't know if that's somebody's phone, another earphone, but sorry about that. This was based off 1 second of dress time, and it shows you as the gun pressure goes up, the cutting amount will go up. The reason that's important is because, as you can see, time is very valuable to all of us in this industry. This is just an example of 100 kgf, about 200 pounds of pressure, and 400 spot welds. You can see 0.5 cleaned it up pretty nice of dress time, 1 second of dress time also. But really, we don't want to spend this much time at the dresser. We want to do it quickly, and we'll talk about how to do it quickly in the next few slides. As I said earlier, one of the most important things is cutter selection. And the reason it's so important is, like I said, there's thousands of different cap tip configurations. There's thousands of different gun angles and gun figures that we have to deal with on a daily basis. So as you can see, there's many different kinds of cutter blades. You have a single blade there. You have a double blade here. Some people have a 4-edge blade. There's different material kind of blades. There's a reversible blade. So there's many different blades that you can come up with. The most important thing is just to be sure to come up with the right one that matches your cap configuration. Because if you do, as you can see, you can have a good condition. And what we want is to get back to that exact original figure. We want it to get back to whatever it was to start with and the same resistance it was to start with. Now, if you choose the wrong selections, hopefully none of you guys have ever seen this, but you can come up with some rough surfaces, some cracks or dents. That's generally from not taking enough off each time. Or you can have the star face figure here, where your cutter blade does not match your cap design, and you cause wobbling or walking, moving around.